At this point, we'll start tabulating some results. I drew up a graph. Here I have a load voltage column, a Zener current column, load current column, and finally a load resistance column. Incidentally, the method I'm using to connect the ammeters and oscilloscope probes to the breadboard is just a simple little thing. I use these wire jumpers and I just bend them in such an orientation it makes connecting the probe tips to the breadboard a whole lot easier. Now this is the oscilloscope probe here, and you can see if you squeeze down it's all there's a spring in there. You can see the tip. I'll just move it out there, you can see it clearer. Okay. That helps you make a connection. Now I just connect that onto the wire jumper. It's a lot easier than trying to fool around with this, but we'll continue on. Okay, now in order to tabulate some values, I've set up two multimeters. I have a multimeter set up to measure the current through the diode, these two ends here. I have another multimeter here set up to measure the voltage across the diode. The first reading will involve no load resistance, and then we'll start adding load resistance and see what values we get. Okay, these values are looking good. 5.27 volt drop across the diode, the Zener diode, and we have about 33.3 milliamps flowing through the Zener diode. Now I'm just going to put different load resistance values in, and we're going to keep an eye on the current and voltage. The current will always be through the Zener diode at this point, and the voltage will be the voltage drop across the load resistance. I'm going to put 70 ohms in first as a load resistance. Let's see what value we get. Okay, now that doesn't look good at all. You have a 2.6 volt drop across the load and 0.02 milliamps flowing through the Zener diode. The diode is not working at this point, and I'll explain why later. Okay, we'll step it up from 70 ohms to 100 ohms. Let's see what value we get. Okay, again not looking good. We have 0.26 milliamps flowing through the Zener diode and a 3.65 voltage drop across the load, nowhere near our 5 volt mark. Now I'm going to step it up from 100 to 200 ohms. See what we get. Okay, looking much better. We have a 5.07 volt drop across the load and 8.4 milliamps flowing through the Zener diode. That's for 200 I might, yeah, I'll just go, I'll do one more. I'll do a 300 ohm load and see how we go. I'll leave it at that. And just set this up. 300 ohms coming up. Okay, that's 300 ohms. 300 ohm load resistance, 0, and we've got 5.21 volt drop across the load and a 15.8 milliamps flowing through the Zener diode. Again, it's keeping it's at our desired voltage, approximately 5 volts. And 15.8 milliamps. That's at 300. Okay. Here are our final tabulated results. As you can see here in the load voltage, we have 5.07 volts and 5.20 volts. That's approximately 5 volts. These are acceptable. And what is important to realize here is that those values are satisfactory because here the Zener current is above that 5 milliamp design criteria that we worked out earlier on, that we used to work out the resistor and capacitor values. Here we've got 8.4 milliamps and 15.8, but however here it falls below the 5 milliamps. You've got 0.25 and 0.02. As a result of that, you get the lower 3.65 volt and 2.6 volt readings. Over here in the load current, you'll see here that from this row downwards, it's well below the 30 milliamp design spec that we wanted to incorporate into the design earlier on. We said that we're going to go for a maximum of 30 milliamps. 25.1 here, 17.2. However, up here, you see we've gone above the 30 milliamp maximum. We've gone to 36, 38.4. By the way, that 30 milliamps, to get exactly 30 milliamps, you're looking at a load resistance of about 170 ohms. Okay, now I'm just going to show you a graph of what our problem is, why we keep on getting these incorrect results for values lower than 5 milliamps when 5 milliamps passes through the Zener current, through the Zener diode. This is the current voltage curve of the Zener diode, the 4733A. For correct operation of this Zener diode, you need to be in the steep region here. In the steep region, the RZ value is about 7 ohms. And here the slope is equal to 1 divided by RZ. So the smaller the RZ value, the steeper the slope. What happened before, when we got those incorrect results, we went below the 1 milliamp region. The IZK value at this value here, at 1 milliamp, the RZ value, the dynamic resistance, is about 550 ohms. So we had a larger value than that, which caused us to have a shallow slope. The steeper the slope, you see that even for a large change in current, you're going to get a relatively small change in voltage. Whereas if you're up here, even for a very small change in current, you're going to get a relatively large change in voltage. So, for correct operation, this region here, we chose a minimum of 5 milliamps, which is well above the 1 milliamp here. So, we're well within the correct region for operation. The IZT value, well, that's the test current. At the test current of, well, here 49 milliamps, you get the rated voltage drop for the Zener diode, which is 5.1 volts. When I tested it at 49 milliamps, I got about 5.3, 5.2 volts, which is within the tolerance for this component. So there you go, that's the end of our project, the end of the video. It highlighted some steps involved in design. It also showed some of the instruments one can use in order to confirm correct operation of the circuit, the oscilloscope and the common multimeters. Yeah, so if you liked it, let me know. If you don't, let me know how I could improve. And you can also make some requests. If you'd like to focus on some of the components themselves, let me know. If you'd like to go through another circuit, try and design and build another circuit, let me know, and hopefully I can do it. Well, anyway, I hope you liked the video. It was my first video. Thank you.